right, so let's continue on with that 7.8 where we were looking at Le Chatelier's principle and how we can put a system, an equilibrium system, under a stress. Okay? I wanted to point something out about this reaction. Notice we used, this was a nifty little one for using volume, because it's going to affect it because we have 4 moles of gas on this side, 2 moles. So if you decrease the pressure or increase the volume, it goes this way. If you increase the pressure and decrease the volume, it goes that way. But this reaction is worth talking about a little bit. It is one of the most famous chemical reactions. So the video after this kind of talks a little bit about why in the world is this taking a little bit of nitrogen and hydrogen and getting them to come together and make ammonia. Why was that so challenging, and why was it so very, very important for us as a species? So anyway, so that's something you're going to be working. You're going to watch that video after this one. That's the third video. So the other thing you can do, of course, which is a little more obvious, you can dump in some reactants. It goes away from where you dumped in the reactants. Okay? If you dump in products, it'll go away from where you dumped in the products, because you'll be heavy on the products and it'll shift left. Dump in the reactants, it'll be heavy on the reactants, it'll shift right. So a situation like this, again, using this very famous reaction, it's going to say, okay, at equilibrium, we have this kind of thing going on, and what we've done here is we're going to take this same system, but we're going to add a bunch of NH3. So you're going to dump a bunch of NH3 on there. So the NH3 it's heavy on the product side. Therefore, it wants to kick back to the left once you do that, and the reaction will compensate by going back and to the left. All right? Too many products, it'll fix itself. And that's what Le Chatelier is all about, is throwing off the equilibrium system and predicting how that is going to be fixed. Okay? So if you add more products, it goes away to the reactant side. Okay, now, this one's a little trickier. If you decrease one of those, it kind of fills the open hole. So if you take away, it'll fill that up. I got a good analogy for this one. When I was in high school, we had chickens, and we did free-range eggs. And one of the things I learned is I had to find where their nests were, because if they hid their little place where they lay eggs, and they sit on those eggs, they stop laying eggs. And the other ones hatch, and it's kind of hard to sell eggs when a little half a chicken falls out of there. So we had to be very meticulous about knowing where those places were and collecting them on a very regular basis, because the chicken, interesting fun fact, shuts off its egg-making mechanism. If it's sitting on an egg, it can kind of feel that, and it's like, okay, I'm good for a while. And if it sits down, no egg, this is an evolutionary thing, then it's like, I got to make another egg. So it'll continually do that. So reason I bring that up is if you take something away, you'll get more of it. You'll get more of what you take away. Okay? So a lot of these reactants, if you want the product, you have to take that product away, leave a space, and then it'll proceed to the hole that you just left. Okay, so we have this same system, and let's say you remove a bunch of NH3. Okay, so you remove this NH3, and this is, by the way, it's not 7 moles. You're like, hey, there's only this 2. It's 7 actual ammonia molecules have been removed, and now you're heavy on the reactant side. So it'll shift and go back to equilibrium by going to the right. You took away an egg in ammonia, what'd you get? More ammonia. Take it away, you get more ammonia. And then in this reaction, it's very easy to do. All you have to do is put a little water in there, and ammonia is extremely soluble in water, and it just disappears as it's made, driving the reaction forward. So that was an important discovery. Looking at number of particles, you just want to get to the point where it's going to shift. Now, what if you add a solvent? Okay, so you have a situation where those ions are on both sides, and then all of a sudden you dump in a bunch of solvent. Well, what's going to happen there? It's good to see an example to fully understand this. The reaction will proceed toward the side that has more ions or more particles, which of course in this situation most of the time is going to be ions, and it will proceed and sort of compensate in that direction, because now you got a whole lot more water molecules to surround these guys. If you remember the solvation energy, where water molecules surround those little guys and keep them from getting back together, sort of prevent them from going back this way. So water is a huge part of this. Of course, solvent is what we'd be looking for. Okay, so one of the ways to get to drive these reactions forward is to just add a little bit of water. Okay, so temperature, again, kind of a tricky one, but the way I want you to think of this is, so we're using that same reaction, that same famous reaction. You're going to find out in just a little bit why it's so famous. It's an exothermic reaction. So you have to know where the heat is in the reaction. Let me explain that. So if you're going to remove the heat, that's what you do when you cool it. It's like taking the egg out on the right side. And if you remove some of the product, it'll fill the space. So think of this as being one of the products, but it's energy that you can remove by cooling it. And you leave a space, and it drives the reaction forward. Well, you can imagine their surprise. They kept heating it, trying to get more product, and the more they heated it, the less product they had. Okay, so this is why this is such a good example of Le Chatelier's principle. Okay, so heating it, you're adding to the same side. It's like adding more product. When you add more product, it will shift to go away. Add here, it goes away. Take away, it comes back. So you got to know if it's exothermic or endothermic in order to be able to answer those questions. So you have something like this, and we're going to do this demonstration for the students in class. It's just a big tube that has sort of a tan-colored gas, and you're either you heat it or you cool it. What's going to happen? Okay, so right here you can see this is given the fact that it is positive, gives that it is endothermic. Okay, so that means the energy is over here. The heat is over here. So what's going to happen? What would occur if the temperature of the system increases to 75 degrees? Well, you have the heat's already over on this side because it's endothermic. You had to know that, right? Plus, over on this side, add heat. It'll go away from where the heat is, and the reaction will proceed to the right. And when it does that, it'll become darker brown as a result. Okay? So that's all we're doing is we're taking these big tubes and dropping them in hot water and cold water, and I'm going to have them predict whether it's exothermic or endothermic, and they have to know if it turns more brown when you heat it, it's endothermic. Okay? So the next part involves a little more detailed problem, so we're going to start next class with the pH scale, and we'll finish up the lecture and finish up the problem set. So we're halfway through. You're going to watch this video and then that short video about that magical reaction, and take some notes down about that too, just in case you see that again. You have enough technology to get through about the first 10 problems. I'm kind of hemming and hawing about whether we're going to do the lab Tuesday, Thursday of next week, or Friday, Monday. So I'll keep you posted. I have to kind of hash out the whole schedule. But we do have one more lab we're going to do, and we will get that exam in on equilibrium before the break. We're going to be doing just a little bit of work over break to kind of keep on track. This is that point where I have to kind of look at what we can accomplish moving forward. So this one, we're about halfway through 7-8. You can get about halfway through the problems. So obviously nothing to submit, but again, make sure that you're understanding this stuff. Le Chatelier's principle. Maybe get through those questions that deal with Le Chatelier's principle, and make sure that you really, really try them before you look at the answer key, to make sure, because it's pretty much a right or a left or a nothing, so it doesn't hurt to guess on some of those. And if you don't understand the reasons, we need to ask questions on this stuff. So starting to get moving toward this next lecture is really more the advanced stuff on equilibrium chemistry, to sort of tie a lot of these concepts together. All right, so happy Thursday, and get going on about half of your problems. Bye.